Welcome back to Maths for Mrs. J. In our previous video, I taught you how to go from Cartesian form to polar form. I did the harder one first, so I did you a bit of a favour there. Now we're going to go back the other way. Just remember that in polar form, what you're talking about in essence is what angle in radians you have moved anti-clockwise from the positive direction of the real axis. And that's called your angle or your argument. And your magnitude or modulus is how far you are from the origin. We found that by doing our square root a squared plus b squared because we know that Pythagoras' theorem holds due to right angled triangles. So down here, if we wanted this back as our a plus bi, we would know that this length here is B and this length here is A, and this is a right angle. So we know that A squared plus B squared is R squared. We already know that. So we know that R is the square root of A squared plus B squared. That's all good. And we know that tan of theta is our B on A. But remember, we had to be very, very careful about doing inverse tan, because if you do inverse tan, A, on your calculator, it's unlikely to give you an exact value, and we want to deal in exact values if we possibly can. But B, your calculator will only give you, when it does inverse tan, it will only give you a value between 0 and pi. So if your B on A happens to be positive, it's going to assume you're in the first quadrant. You might actually be in the third quadrant, okay? In which case you will need to adjust your angle. If B on A is negative and you do inverse tan, your calculator will assume you're in here, but you might actually be in here. So always draw a little diagram. It doesn't have to be fancy. Just draw a little diagram to help yourself out there. Okay, let's go back and I'll show you how to get from our r cis theta back into our a plus bi. So we said that z is our r cis theta. And we said that that means r cos theta plus I times r sine theta. Okay, now clearly our real part is our A. We want to have A as our real part, and our imaginary part is our B. Well, if we already know this angle here, and we know what R is, we can simply multiply out and work it out. It's really not that hard. I'll show you how to do it. Let's do an example. Okay, let's have a look at this example. It's a good idea always to have a bit of a diagram happening so that you can see where you are. Remember what I said before about the inverse tan business. So we really need to have a clear idea about where we are. So let's just draw a little diagram. It doesn't have to be fancy. And so this is our real axis, this is our imaginary axis. So if we're at negative 2 pi on 3, we're heading in this direction by 2 pi on 3. Now this is 1 whole pi, so 2/3 pi would be around here somewhere, wouldn't it? Let's just pop in the line from the origin to this point. So what we're interested in finding out, of course, we know that this length here is 2, and we know that this angle here is 2 pi on 3. And what we're aiming to do is to find, if you like, the x and y values of this point. We're trying to find the real part and the imaginary part. Now let's just think for a minute about how this is going to relate to our horizontal axis. If 2 pi on 3 is to here, then this little bit in here will be pi on 3, which means that the equivalent first quadrant triangle that we're looking at is pi on 3. Just remember that for when we're working this out. All right, so let's do our expanding. So 2 cis pi on, negative 2 pi on 3, sorry, is 2 times cos of negative 2 pi on 3 plus I times sine of negative 2 pi on 3. And here is where being up to date with your trigonometry is very handy. Cos of negative 2 pi on 3, remember the old horizontal reference business, it will be the same as cos of pi on 3, but it will be negative. So this will be negative a half. All right. Sine of negative pi on 3 will be the same in magnitude as sine of pi on 3, which is root 3 on 2. But it will also be negative. Then we can just multiply through by our 2 and we end up with negative 1 minus root 3i. Does that make sense? Yes, we've got a negative real part and a negative imaginary part, so all good there. Okay, let's have a look at our next example. So again, it's a good idea to get a little sketch happening just to see where you are in the whole scheme of things. So we've got our real axis and our imaginary axis. And we're talking about 7 pi on 6. Okay, 7 pi on 6 is here somewhere, isn't it? So let's put in our line. And our angle is going to be all the way around here is 7 pi on 6. So what's this little bit of angle here? Now I know I've drawn this the same as that, but the drawing is really more to show you about what quadrant you're in than exact sizes of angles, so forgive me there. That means 7/6 is 1 and a 6th, isn't it? So this will be pi plus pi on 6. And we know that this length, the distance, magnitude, modulus, whatever you want to call it, that length there is 3. So doing our horizontal reference, thinking back to my unit circle videos, when we expand this out, so we've got z equals 3 times, okay, cis means cos plus I sine, so cos of 7 pi on 6 plus I sine 7 pi on 6. And we're going to end up with 3 times. Okay, now cos here will be the same as cos of pi on 6, but it will be negative. So it'll be negative root 3 on 2 plus I times, same thing with sine. It will be the same in size as sine of pi on 6, but it will also be negative. So when you multiply through, we're going to get negative 3 root 3 on 2 is our real part, minus 3 on 2i, 3i on 2, doesn't matter. Let me just show you one more just for interest. What if I said z equals 5 cis pi on 2? What do you think about that one? See what we can come up with there for our picture. Where is pi on 2? Pi on 2 is here. I've gone and done it in an arrow. I didn't mean to do it in an arrow. It's on the imaginary axis. So when we actually expand this out, we get 5 times cos of pi on 2 plus I sine pi on 2. Well, cos of pi on 2 is nothing, 0. Sine of pi on 2 is 1. So all we end up with there is just 5i, which makes sense because we're just on the imaginary axis.